In this video, we aim to justify the method of solution for second-order differential equations of the form a d2y dx squared plus b dy by dx plus cy equals 0 that we met in the previous video. So, the differential equation a d2y dx squared plus b dy by dx plus cy equals 0 has as its auxiliary equation the quadratic equation am squared plus bm plus c equals 0. So let's suppose that alpha and beta are the two roots of the auxiliary equation. And for a moment we are going to suppose that y is linked to another variable z by the relationship y equals e to the alpha x times by z. Now if this is the case, then the product rule gives us that dy by dx must be alpha e to the alpha x times by z plus e to the alpha x times dz by dx. Differentiating again using the product rule, we get that d2y dx squared must first of all be alpha squared e to the alpha x times by z plus alpha e to the alpha x times by dz by dx. So those two terms are the result of differentiating alpha e to the alpha x using the product rule. Then we must differentiate e to the alpha x times by dz by dx, again using the product rule. So that will give me alpha e to the alpha x times by dz by dx plus e to the alpha x times by d2z dx squared. And we can tidy up this expression for d2y dx squared to obtain alpha squared e to the alpha x times z plus 2 alpha e to the alpha x times by dz by dx plus e to the alpha x times by d2z dx squared. So this enables us to rewrite the equation for y as a new equation which will be slightly easier to solve in terms of z. So the y equation was a d2y dx squared plus b dy by dx plus cy equals 0. Substituting in for d2y dx squared dy by dx and y, we obtain a times the expression for d2y dx squared plus b times the expression for dy by dx plus c times y, which is simply e to the alpha x z, must equal 0. And if we collect together the similar terms, we've first of all got e to the alpha x z times by a alpha squared coming from the first bracket plus b alpha coming from the second bracket plus c e to the alpha x z coming from the final term. Then collecting together the e to the alpha x times dz by dx terms, we get e to the alpha x dz by dx times 2a alpha from the first bracket and b from the second bracket. And then finally we've got a e to the alpha x times by d2z dx squared. Now we can clearly divide the whole of this equation through by e to the alpha x to obtain z times a alpha squared plus b alpha plus c plus dz by dx times 2a alpha plus b plus a times d2z dx squared equals 0. Now at this stage we need to remember that alpha and beta are in fact the roots of am squared plus bm plus c. So we certainly know that a alpha squared plus b alpha plus c must equal 0. What's more, we also know that minus b over a must equal alpha plus beta. So b must be equal minus a alpha minus a beta. So 2a alpha plus b can be rewritten as 2a alpha plus minus a alpha minus a beta, which leaves us up with a times alpha minus a times beta, or if we like, a times alpha minus beta. So our differential equation in red will now become 0z plus a times alpha minus beta times dz by dx plus a times d2z dx squared. And we can divide this equation through by a to obtain d2z dx squared plus a times alpha minus beta dz by dx equals 0. So, taking this equation now, in the first case we'll look at what happens if alpha and beta are two different numbers. So, we can take the equation d2z dx squared plus alpha minus beta times dz by dx equals 0 and simply integrate it with respect to x. Integrating d2z dx squared gives me dz by dx. Integrating alpha minus beta times dz by dx gives me alpha minus beta times z, and integrating 0 just gives me a constant. So I've got dz by dx plus alpha minus beta times z equals p, where p is my constant. And this is a differential equation of first order which can certainly be solved using the integrating factor method that you met in an earlier video. The integrating factor for this particular equation is going to be e to the integral of alpha minus beta. The integral of the alpha minus beta is simply alpha minus beta times x, so the integrating factor is e to the alpha minus beta times x. Multiplying the equation through by the integrating factor gives me e to the alpha minus beta x, lots of dz by dx, plus alpha minus beta times e to the alpha minus beta x, lots of z, equals p times e to the alpha minus beta, lots of x. The left-hand side of this equation is an exact derivative. It's the derivative of e to the alpha minus beta x times z. So we've got the derivative of e to the alpha minus beta x times z must equal p times e to the alpha minus beta x. Integrating each side, the left-hand side simply becomes e to the alpha minus beta x times z. The right-hand side becomes p over alpha minus beta times by e to the alpha minus beta x plus a constant that we're going to call q. We can divide this through by e to the alpha minus beta x, which if you like is the same thing as multiplying through by e to the beta minus alpha times x. And that will give us z equals p over alpha minus beta plus q times e to the beta minus alpha x. Now remember that y was equal to e to the alpha x times z. So we can now get back to what y must be. So y is e to the alpha x times our previous answer for z. So what we've got there when we multiply the brackets out is we've got y is p over alpha minus beta times e to the alpha x plus q e to the beta x. p over alpha minus beta is simply a constant. So what we can say now is what we've got is that y must be of the form a times e to the alpha x, where a is a constant, plus b e to the beta x, where b is also a constant. So we've dealt with our first case where the two roots are different. Moving on to the second case where the two roots are the same, where alpha equals beta, well, that makes life even easier because the equation that we've got now just becomes d2z dx squared plus 0 times dz by dx equals 0. So d2z dx squared equals 0 tells me very quickly that dz by dx must just be a constant, call it p. And integrating again now tells me that z must be equal to p times x plus another constant, call it q. So we've got z is px plus q, which now means, if we remember that y is equal to e to the alpha x times by z, that we've now got y is e to the alpha x times by px plus q. In other words, we've got y equals px plus q times by e to the alpha x. So we've shown that this must be the solution if we've got equal roots to the auxiliary equation. Finally, we need to think of what happens if the roots of the auxiliary equation are complex numbers. Well, since a, b and c are real numbers, if the equation am squared plus bm plus c equals 0 has complex roots, then they must form a complex conjugate pair. So let's suppose for a moment that the two roots are alpha, which is equal to lambda plus I omega, and beta, which is lambda minus I omega. Then, from what we've already done, that suggests that the solution of the equation ought to be of the form y equals a e to the lambda plus I omega times by x plus b e to the lambda minus I omega times by x. Now, we can split the exponential terms up. So e to the lambda plus I omega times x is going to be the same thing as e to the lambda x times by e to the I omega x. Similarly, e to the lambda minus I omega x is going to be the same thing as e to the lambda x minus e to the lambda x times by e to the minus I omega x. So we can take out a factor of e to the lambda x. So we've got y equals e to the lambda x times by a e to the I omega x plus b e to the minus I omega x. Now, in a much earlier video for this unit, you will have come across the result that e to the I theta is the same thing as cos theta plus I sine theta, and e to the minus I theta is the same thing as cos theta minus I sine theta. So, we can rewrite our expression for y as being e to the lambda x times by, first of all, a cos omega x plus I sine omega x, add b cos omega x minus I sine omega x. Tidying that up a little bit, we can now say that that must be e to the lambda x times by a plus b lots of cos omega x plus I times a minus b sine omega x. Now, for all values of x, our solution to the differential equation, y must be a real number. And that tells me that if I put x equals 0, then y is just going to be equal to a plus b. So we certainly know that a plus b must be a real number. Now, if we put x equals pi divided by 2 omega, then cos omega x is going to be 0, and sine omega x is going to be 1. Which means that y is going to be e to the lambda times pi over 2 omega, lots of I times a minus b. Well, e to the lambda pi over 2 omega is certainly a real number, so I times a minus b must be a real number, since y must be a real number. So, we know that a plus b is a real number, and we know that I times a minus b is a real number, so we can say that we must have y equals e to the lambda x times p cos omega x plus q sine omega x, where p and q are real constants. So, what we've managed to show is that if the roots of the auxiliary equation are alpha and beta, then the solution of the differential equation will be a e to the alpha x plus b e to the beta x if alpha and beta are distinct. It will be px plus q times e to the alpha x if alpha and beta are the same. And if alpha is equal to lambda plus I omega and beta is equal to lambda minus I omega, then the solution of the equation is e to the lambda x times by p cos omega x plus q sine omega x. And these were exactly the three results that we had set up in the previous video. So we've now justified our solution method for finding the general solution of the second order equation a d2y dx squared plus b dy by dx plus cy equals 0.